interesting and actionable webcast. Now soon we're going to hear from an expert in the area of Wi-Fi connectivity, and part of what he is going to discuss are the results of a unique, high-speed, 3-stream enterprise user access test with results that very well may surprise you. Now we're going to suspend that surprise for just a little bit because I've got a couple housekeeping items to take care of. First of all, if you have any pop-up blockers turned on, I'm going to ask you to turn them off, and that way you'll be able to leverage the full benefits of the player that you're looking at right now. Secondly, if you want to look at the slides in full screen mode, there is a full screen button that you can toggle back and forth between full screen and the partial screen with the slides once we start going through them. Finally, you're going to notice a resources area of your player where we've loaded in some additional resources to enhance your knowledge of the subject matter, and I'll have more specifics on what's in there a bit later on in the webcast. All right, so with that out of the way, let's meet our special guest speaker, who is Cameron Dixon. Now, Cameron is a graduate student at Syracuse University's School of Information Studies in the Telecommunications and Network Management program. While taking the iSchool's Enterprise Wireless course, Cameron was invited to be a participant in the wireless testbed of the iSchool's Center for Convergence and Emerging Networking Technology. Cameron, thanks very much for taking time in your busy day to join us today.
Thanks for having me, Bill.
So tell us a little bit about the test, about Syracuse University, and a little bit about why Syracuse was the test site that was selected.
So these tests are high-density tests of multi-clients, multi-access points. The goal is to see what an enterprise can experience in terms of a high-density deployment in wireless. Let me tell you briefly just a bit about Syracuse. Syracuse has been around for 140 years or so. We have a large student body and staff. The information school is pretty highly ranked. Professor Malta, Dave Malta, who was the investigator on this project, he is the director of the undergraduate program for the iSchool and also teaches at the graduate level. He has been around at the school for a number of years and has written focused on wireless deployments. He's been interested in that space for some time. He's previously been writing for network computing and other networking magazines. And so he has a good track record of following the industry and of guiding students to this space. So Professor Malta was approached by Ruckus Wireless with an interest in performing these tests, and he rounded up a group of students who were in his class to participate in this test bed.
And you were able to simulate, given the size of Syracuse, essentially you were able to simulate an enterprise environment, is that correct?
Yeah, these tests were performed in Heinz Hall, which is the home of the School of Information Studies. And of course, to facilitate Wi-Fi testing, you have to have a clean environment. And so these tests were performed at night with the campus wireless network. Of course, the campus has a wireless network brought down so that we could perform these tests.
Excellent. Okay, so Cameron, can you give us a kind of a quick summary and overview of the results that you got?
Sure thing. So these tests were performed by us at Syracuse University. Now we have independent, perhaps in scare quotes there, because these tests were performed, they were selected by Ruckus Wireless, but the outcome was not determined at the start. These are the tests that they were interested in, but they were not involved in the rigors of testing. Other vendors additionally were solicited. We asked for their opinion. With some response, Meraki particularly was very helpful in assisting with client configuration. The important thing to recognize is that you're going to have wide variations between what vendors claim and what the actual performance of your access points are going to be. This is because the data rate of an access point is going to be different than the throughput of an access point. And this is largely due to your layer 2 retransmissions, to all of the overhead that goes into making Wi-Fi work. You've got contention mechanisms, you have aggregate frame acknowledgements, you have management frames that need to occur so that you can have connectivity at Wi-Fi. The distinction between data rate and throughput is generally what your applications are going to experience. Data rate is simply what happens at the physical level. It's a theoretical construct that's possible, but because of overhead at layer 2, you're going to experience a decrease. Another finding is that as your distance and as the number of clients increases, your performance is going to degrade. This is simply a matter of the radio frequency and how this happens when you have additional clients on your Wi-Fi. you're essentially dividing your throughput by the number of clients that you have. And so it makes sense that as you have rooms that are further away and you have rooms that have increased clients, your performance is going to drop. The Ruckus access point didn't have the highest aggregate TCP throughput in all of these tests, but generally it did and performed very well, very consistently throughout these tests.
Excellent. So, and just to reiterate, as you said, Ruckus was heavily involved from the outset, but that the tests were all conducted independently by you folks. Nobody was leaning over your shoulder, pulling switches and telling you what to do. That was all up to you folks, correct?
That's correct. The outcome wasn't determined at the outset.
Excellent. Okay. So what were some of the test performances that you observed?
First, let me give you an overview of what the access points were. As I mentioned, the goal was to determine what's realistic here in an enterprise environment of 3-stream access points. We selected 5 access points. These are generally the market leaders in Wi-Fi. We had Aerohive's 330, Aruba's 135, Cisco's 3602i, Meraki's 24, and the Ruckus 7982. There were 3 tests performed. I'll give it just a high level now. We had a single AP test with a single client. This is a small white lie because these are dual band tests, and so you have to have dual clients as well, which I'll explain in a bit. Single AP with multiple clients. This is where we have a single access point across multiple rooms. This is a total of 90 clients for the second test. The third test, there were a total of 6 access points spread across 6 different rooms, although clients were in 4 rooms. There were 120 clients in this third test. So again, on an aggregate level, you can see here that out of our 87 tests across these 3 evaluations, Ruckus had the highest aggregate TCP performance, 66% of the time. That's a pretty incredible number, especially compared to how these other vendors did. This is just a breakdown of our multi-client and multi-AP tests. On the left side, these multi-client tests represent our 90-client tests. So 83% of the time, Ruckus had the highest aggregate TCP throughput. Just to be clear, down at the bottom where it has 0%, that doesn't mean that these vendors didn't perform. That simply means that they didn't have the highest aggregate TCP throughput. They didn't have a win. On the right side, here are multi-AP tests. These are 120 clients. So 58% of these 30 tests, Ruckus came out on top.
Cameron, these are some pretty big names in access points that you tested that Ruckus went up against. Did these results surprise you?
Yeah, I think generally our team, I suppose, perhaps indoctrinated by others, we expect the market leader, which is generally Cisco, to perform on top. And that simply wasn't the case. Generally here, the Ruckus and the Aruba APs outperformed the rest. And then with the Ruckus AP generally coming out on top, we were impressed by these findings.
Well, let's dig into a little bit more detail on the tests themselves, if you would, and tell us what you did and what are some of the things that you found.
You bet. Let me tell you about the methodology, how we go about systematically evaluating these tests. The goal, of course, as I mentioned, is to test in a real environment, tested in Heinz-Hall, which I'll show you in a minute. We modeled these tests after how deployments will technically be set up within an enterprise. So that goes as far as setting our channel bandwidth the same as an enterprise is going to be, setting our clients in a manner that is going to be typical in an enterprise environment at a desk, setting the clients typically in a laptop. You're going to have your antenna within the screen, so that how you set up the screen also matters. We try to set it up in a way that is realistic for those enterprise environments. The goal here is not simply to get Wi-Fi coverage, but it's about capacity. This is generally true of all spaces that have wireless deployments now. It's not so much about being on the Wi-Fi, it's about having a decent experience. This becomes an increasingly important factor as you increase the number of clients, as you have high-density environments where you have increasing numbers of wireless clients, that your aggregate throughput is going to be divided by the number of those clients. And so having a decent capacity, having a high throughput, is generally important because the number of clients on wireless LANs are increasing. It's important to do these tests, as I've mentioned, because what vendors claim is not going to be actual throughput. Generally, you will see access points that will be marketed with 450 megabits per second per band. Sometimes this is aggregated. It'll show on the box it's just 900 megabits per second. This is simply not realistic, as I've mentioned before. because those are the data rates, those are at the physical layer, where what you're actually going to experience is going to be the throughput of these devices. And those 900 megabits per second or 450 megabits per second are not quite realistic. Additionally, in an enterprise environment, those numbers account for physical setups that aren't practicable. What I mean by that is that in an enterprise environment, you can set up at 2.4 gigahertz, which is you have two bands in Wi-Fi. You have 2.4 and 5 gigahertz. In 2.4, you can have the same 40 megahertz channel bandwidth as you do at 5 gigahertz, but it's really not practical in an enterprise environment because of your channel reuse plan. You won't have enough channels to be able to facilitate a wide deployment of access points. So this comes into account of what actual throughput is, how you actually physically set it up, and we tried to model that in these tests as well. Typically when an enterprise is testing out access points, they will put an AP up on a stick and a client out there, just one client, one access point to test how an access point acts in their environment. And that's important to do because it gives you a baseline for what kind of signal strength you can expect in your environment. Enterprises in their environment should figure out what the map is going to look like of their signal strength. But that doesn't really scale very well when you have multiple clients. And then when you have to take into account a channel plan for your access points. All of that has to be considered. Because that's difficult to do, and because vendors don't often send out to test multiples of access points, we wanted to set up an environment where we could test those out and figure out what the results would be for enterprise environments. Let me explain a little bit about what stayed true across these tests before we break into what these tests actually were. These tests were performed at night, generally between the 11 o'clock and 7 a.m. hours. We used a spectrum analyzer to run through our environment to ensure that we had a clean RF environment. We used Metageek's Channelizer. Additionally, we used all three-stream clients. Now, three-stream clients are increasing in the marketplace and in the enterprise, and three-stream clients are becoming the norm. We wanted to take advantage of every capability that these access points could serve to us, and that required us to use three-stream access. And that required us to use three-stream clients across all of our devices. A bit about our test software. We used Xchariot. We used the throughput script, which is just a script that's just by default available in the program. For our multiple access point tests, we used a 1 megabyte file transfer, and all of these tests were done for the duration of 2 minutes. In our single client, single AP tests, we used the high performance throughput script. This was a 10 megabyte file transfer for the duration of 2 minutes. Because clients will roam if you have a single access point, all of these access points allow the capability to have a single access point, but to have 2.4 and 5 gigahertz bands on that single AP. Because we wanted to test individually just what experience would be at 2.4 and also what experience would be at 5 gigahertz, we needed to have one SSID for each band. So we would name these 2.4 and 5 gigahertz so that the clients wouldn't roam across the SSID, across the access points. AP channel selection is really important because it determines whether interference will occur. Your channel selection is an important metric that you need to care for. So in single AP, we use the lowest channels that were on each applicable band. That's channel 1 at 2.4 and channel 36 at 5 gigahertz. For our multi-AP tests, this is the test with 120 clients. We use the radio resource management, the automated channel selection that would occur in each access point. Each vendor has an algorithm that will allow them to set channels on the access point. We let that run for an hour, and then because we didn't want the channels hopping as the test was going on, we set those manually for all of our access points. And again, the unit of measure here, what we're actually testing is the aggregate TCP throughput of each vendor's access point. Here we have some images of Heinz Hall. Here in the top left, you can see our PC clients that we had. We used three-stream adapters for those. You have images here of also our three-stream laptops. We use predominantly three-stream MacBook Pros. On the bottom left, the image shows an example of our single AP tests where you have, this is our long-distance location. So you see our clients there on the left side, and then all the way down the hallway, 105 feet is where the access point is, which is shown in the image there right next to it.
Well, Cameron, it's clear that you and the other testers went through great pains to ensure, as you say, a clean environment and, most importantly, a consistent environment for each of the APs that were tested. Now, I understand the tests were further broken down into 3 segments. If you would just describe the first, which is a single AP, single client setup.
Yeah, you bet. So our first test consisted of a single access point and a single client per radio. This requires 2 clients. So we have single client there, but because we're doing simultaneous tests of clients, we have to have 2. We did tests at the 2.4 gigahertz band, 5 gigahertz, and then simultaneously. There's 135 tests that were done for each access point. This is because there were 5 locations across the floor plan of the basement of Heinz Hall. 3 bands, there's 2 bands, but you have one simultaneous, 2.45, and then both at the same time. So in essence, you kind of have 3 bands. 3 orientations we tested, so our clients were square on with the access point, and then we changed them 45 degrees to the right, and then 45 degrees to the left. There's also 3 directions that we're doing these tests. So we're doing tests from the access point to the client, from the client to the access point, and then a little bit of both. So traffic is going upstream, downstream, and bidirectional. The second test is another single AP test, but with multiple clients. We've got a single AP, 3 different rooms, but 30 clients spread across 3 different rooms for a total of 90 clients. The rooms are at different distances away from the access point. There's drywall and glass and tile that's separating these, so they have different difficulties across the different rooms. And then similarly, we're performing tests at 2.4, at 5, and then both simultaneously. Our final test is the most high density, with 6 access points and 120 clients. We've got 4 different rooms that the clients are in, 6 different rooms that the access points are in. Those additional 2 we allow for client load balancing, which was turned on all the access points, band steering as well. We performed tests both with and without an interfering Wi-Fi neighbor. We had an access point that was simply transmitting to a client. We had 2 clients that were transmitting the entire duration of the test. This was to simulate a rogue network, how it would affect your deployment. So here's the floor plan for the first test. I've already explained a little bit about the test, 135 for each vendor. We have our closest location of 24 feet, 33, 58, and 36. These 4 closest locations, in our write-up, we've actually aggregated these. And this is generally because these distances and these difficulties are what is going to be typical of a coverage-based deployment. These are all close enough that you can anticipate somewhat similar speeds throughout these distances. The long-distance location we included as well to really test these access points and see how effective they could be at these long ranges as well with these short distances. So to give some results for our single AP, single client tests, you can generally see that the Aruba and the Ruckus APs are right neck and neck. This is the short distance location, 24 feet, so this is the closest one. This is also our dual band test bidirectional. So these are both 2.4 and 5 at the same time with traffic both going up and down. And this is pretty typical in an enterprise environment where you're going to have clients sending traffic upstream to the access points, and they're also going to be downloading as well. This is an image of the next location results. This is for the medium distance, 58 feet. Again, you have the Ruckus and the Aruba APs that are right there neck and neck. You can see, again, as distance increases, all throughput decreases. For the long distance location, this is the one that's 105 feet. You saw an image earlier of the client all the way down the hall. Ruckus was at 228 megabits per second, with Aruba falling to 184 megabits per second. Again, all clients fall with the distance, but the Ruckus AP hangs on even with that longer distance.
So in this first test, single AP, single client performance, it's actually surprising to me just the amount of difference, the margin of win, as it were, of Ruckus over all of the others. Again, I'll ask: was this something that kind of surprised you folks?
Yeah, generally, the things that we've learned about the Ruckus access points is that the company spends a great deal of time spending more time on the radio than it seems the other vendors do. where many vendors might get chips from Atheros or Qualcomm or Marvell and simply plug that reference design right into their antennas. It seems like Ruckus spends a lot of time optimizing that and ensuring you have a good balance. And so their performance generally was much better than the other vendors, where it appears they don't spend as much time with in radio frequency land. Many others are simply just plug and play.
Excellent. Okay, so on to test 2, which was a single access point multi-client.
The test 2, this is again where we have 90 clients, 30 clients in a room. We have set up similarly to the previous test, where we're doing tests on 2.45 and both at the same time, bidirectional as well. It's important to understand we have multiple clients. All of our clients are associated, so all 90 clients are associated with the access point, even though they're not being tested. And this is typical even if your clients aren't sending things and they're not downloading things. They're typically going to be associated. So this was, again, to simulate what would be done in an enterprise environment. We performed 4 evaluations in test 2, one of room 1, and then room 2, room 3, and then finally all of the rooms together to simulate a high-density deployment. The distances that are noted here, this is from the center of the room, so 20 feet in room 1. These were PCs that had USB adapters. Room 2 was our laptop room with 45 feet from the AP. Room 3 was 55 feet from the access point. This is another instance where we used the lab computers, 30 PCs with 3 stream adapters. And then finally we tested all rooms with the 90 clients simultaneously. So here's some results from those tests with 90 clients. Ruckus again came out on top. This is the bidirectional test. This is again the short distance, so 20 feet, the room 1. 206 megabits per second over Aruba's 183 and 180. It's interesting to note here, pay attention to Meraki as the number of clients increases. So this is just 30 clients at this point, just 30 clients at room 1. At the next room, we have 30 clients with a longer distance. Meraki falls off pretty precipitously. Ruckus hangs on the top with 143 megabits per second. Aruba with 119. As we go to the next room, as distance increases, Meraki falls off. Now, some of the mitigating factors we took here is that we ensured all of our clients were associated. We would reboot the clients, we would reboot the access point, but the Meraki AP just simply couldn't hang on at this longer distance. Ruckus again comes out on top with 91 megabits per second. These again are just 30 clients. Finally, when we test all rooms at the same time, Ruckus again hangs out on top with 130 megabits per second, but Meraki just simply can't hang on. Similar to the other test, we ensured that all of our clients were associated, but the Meraki AP just simply couldn't handle that many clients and at those distances.
Remarkable, really. I think we're seeing quite a pattern emerging here, Cameron. And finally, your last test, the multi-client, multi-access point test. What were the results there?
So this is the one that I think is most interesting and is of most relevance to enterprise environments. A high-density deployment of 6 access points across 4 different rooms, similar setup to before. We have 2 access points in rooms where clients are not, and this is to facilitate client load balancing. Client load balancing generally allows one access point that has, say, 25 clients on it and another access point that has 5 clients on it to be able to share that load, to be able to basically boot off some of those clients that are still within range of the other access point so that it can share a good experience across all of the clients. We also turned on airtime fairness, and this generally means that instead of making one frame the metric of sharing, of fairness, it makes time and data rate the metric of sharing. So those clients that are essentially able to speak faster because they have a better signal strength are able to do more and get more across the wireless than those clients who have a lower data rate. And these are typical enterprise features that are turned on anyway. So we wanted to see what environments would be like with these features turned on. Similar to before, we have 4 different rooms with a similar setup. And again, as I've mentioned, we've tested both with and without the rogue Wi-Fi network. These 2 PCs were associated with that one network. This is a 2.4 interfering network. they were running an iPerf for the duration of these tests, so traffic was being sent back and forth. So here we have the results for our 120 clients. This is not including a neighboring network. We tested with and without. 562 megabits per second for the Ruckus access point with Cisco at 480. It's important to understand something that's particular to Wi-Fi. Your vendors will advertise data rates, as I've mentioned, often of 450 megabits per second or of 900 megabits per second. When you see that 900 figure, that will often take into account that at 2.4 gigahertz, you will be operating in a channel bandwidth of 40 megahertz. That's simply not practical from a channel reuse standpoint in an enterprise environment. Typically, you're going to be operating in 20 megahertz channels at 2.4 and at 40 megahertz channels at 5 gigahertz. The combination of those for a single access point is about 666 megabits per second. Because we're using 6 access points, our highest theoretical aggregate data rate is approximately 4,000 megabits per second or 4 gigabits per second. That's simply not practical to expect that because of overhead, client contention, and other obstacles that you're going to experience in your environment. Also, with switching, you're not going to experience that because the switches that are behind these access points have a maximum of 1 gigabit per second. So even to reach 562 megabits per second is still pretty impressive. For a single access point would be 666 megabits per second. But to get 562 across 6 of them and to have that aggregate experience for those is still pretty impressive. So these are the results with the neighboring access point. 570 megabits per second. Now, if you paid attention, this is actually slightly higher than the previous number when we had no interfering. We think that this takes into account when the hour under which we had the channel selection, the automated channel selection for each vendor, determine the channel. We think that this probably means, and I say I think because we're not quite sure, we think that this means that the channel selection algorithm for Ruckus particularly was better, which is why it went up. Its channel selection was better perhaps than when it was in a clean environment. And this somewhat makes sense because when you have a dirty RF environment, your channel selection algorithm is able to recognize those channels that won't be clean, is able to mitigate against that, choose channels that would not be non-overlapping from those channels. So the instance where there was a rogue network that slightly went up, not significantly, not really materially either, but it was a distinction here. 570 megabits per second for the Ruckus access point with 120 clients, 6 access points. So it's still pretty impressive that it would reach these kind of numbers across that many clients.
Well, it's pretty clear what the pattern is here, no doubt about it. And this was a very extensive, ruggedized testing, standard across all of these APs, and it's, again, very, very consistent results. But from all this extensive testing, which, as I said, took place over, I think, 6 months, what do you feel, Cameron, were the key takeaways?
Yeah, first I want to explain just a quick caveat. Your mileage will vary. We did these tests in a particular place, in a particular environment. And we believe that these results are born out of long tests. But if you do these same tests in your environment, your experience is going to be slightly different simply by nature of what your floor plan looks like, how clean your RF environment is going to be. We believe that our results will port pretty well, and you're going to experience not similar, maybe not similar numbers, but a similar quality of experience if you test these vendors. It's just important to understand that RF is different per environment, and that how your environment is laid out means you're going to have a different experience. However, it's important to understand just from a summary takeaway that what is advertised is not going to be what is experienced. And this is generally because of how Wi-Fi works, because of all the things that need to occur to ensure that you have connectivity. Your data rate, what's advertised, the physical layer metric, is not going to be your throughput, what your applications are going to experience. And generally, the difference is going to be about 50% of your data rate. So if your data rate is going to be 666 megabits per second, if you have an environment where you have access points at 2.4 and at 5, and a channel width of 20 megahertz at 2.4 and 40 megahertz at 5, you have that 666 figure. For you to experience half of that, so in the range of 300 to 400, is a pretty excellent experience. and the Ruckus AP was pretty consistent in that environment. Rigorous testing is not easy, but it is required. Often people will just do a single AP to test in a single client, and that doesn't scale up very well to a high-density deployment, which is becoming more and more typical, more and more the norm for our environments. Multi-access point tests are important to do. You, of course, have to have multiple clients. When you're just doing an evaluative test, you may not have all those clients. So we wanted to perform this both as a help to those individuals who would be implementers, those that are going to be making purchasing decisions, but also to present these results to these vendors as well, so they can see, maybe that's not quite the results that we were expecting, and so that they can tune and improve their products better. We want to have all of these vendors improve their products. Instrumenting repeatable tests is not easy. It is, number one, not very easy to do these tests in the middle of the night and to be awake after you've had a full day of class. But even so, just ensuring that clients are associated with the access points and that they stay associated with the access points, finding a clean RF environment, all those things are not an easy thing to do. So rigorous testing, doing things effectively and making sure that they're repeatable isn't easy, but it's important. And finally, the Ruckus access point was, as you can see, pretty consistent, and not just consistent, but consistently high-performing throughout all of these tests. That doesn't mean that they won every test. And again, I want to make clear that these were tests that Ruckus was interested in, but that they didn't determine the results of. We performed these tests in an independent manner. And overall, the Ruckus access point is a pretty impressive piece of equipment. So just a brief shout-out to our team. There on top is Professor Dave Malta, who was a facilitator and a great mentor for these tests. From the top and left to right, you had Rensley Pereira, Rohit Sajoria, Harsha Kadia, Rich Vestante, and then on the bottom row, Sneha Fadki. There's me there. Balesh Herv, and Long Ren. I'd be happy to field any requests for information. We do have the configurations for these products that are available on request if you'd like to view those. If you have any questions about these tests or any comments, we'd be happy to hear from you.
Well, Cameron Dixon from Syracuse University, that's just a terrific job of explaining these very extensive tests. And like you said, tough to sit up all night doing these after you've had a day full of classes. But clearly with yourself and the team you had there, just an absolutely terrific job. And thank you very much for your time, and thank you very much for joining us here today.
Thank you very much, Bill, for having me.
And I want to thank those of you in the audience who have joined here as well, and hope that you found this as interesting, certainly as I did. Now, before we go, I just want to draw your attention to the resources area of your player, where we've got a couple items there for you, free of charge. Just all you have to do is click on them. One of them is the slide deck that you heard Cameron go through just now.